So, welcome to lecture number 9. I'm never sure whether I'm counting this correctly. I believe it's number 9 in parallel and distributed computing. And today we continue on what else can we do, Gesundheit, what else can we do for accelerating our code with parallelization. Today I'm specifically going to AVX extensions. However, before we so this is what we are going to do. But before we are doing this, we have an update to the nonsense I told you about threads last time. Because while I was actually giving the lecture, I was stumbling over one thing that I could not explain back then, and I noticed this was really wrong. Yeah. Okay, we come to this in a minute, and then we go to AVX, and we'll do some exercise. I'll show this again later. We'll go to this folder in lecture 9, and there is a matrix multiply which we'll be using for the example of AVX. Okay, so getting to the problem of lecture number 8. So lecture number 8, we talked about threads and we talked about OpenMP, you remember? And in regard with the threads, I told you that there's one alignment that is fast and another alignment that is slow, right? And I also told you this was a little bit counterintuitive to me. And now what you should learn, if something is counterintuitive, then don't just believe it, okay? So it turned out, maybe you remember that I stumbled, when I tried to explain it, I stumbled over this loop here, yeah, where we looped over an index I, and we started with number of threads times the thread ID, and then we looked whether I is smaller than the inner grid size. And this would be, where you start, this loop would start depending somehow on what thread it is using, and it would always go to the very end, right? Which doesn't make sense. So each one should get a slice, right? So the upper bound of this loop should also depend somehow on which threads on the thread ID. So this I could not figure out during the lecture, and of course, during the lecture you want to finish in 1.5 hours. So yeah, okay, this is not. This turned out this is not correct. So in fact, a better solution is to, or actually the correct solution is to get the, to start from your slice. So you have thread ID, yeah, so you'll get, maybe I go to what was actually wrong in the lecture. Yeah, so we pretended that this here. Remember, we'll have here the data is aligned here inside the rows, and we found that if we do the loop inside the columns, then we were faster, which is surprising because this was the thing that is counterintuitive, yeah. And this was faster only because the other implementation, where you go along the array, was implemented in the wrong way. So the correct way is not to use at inner grid size, but at inner grid size divided by the number of threads plus the number of threads times the thread ID. Yeah, so this basically was here the mistake. And if we look at the code, which is this here. So I now corrected this. So where was it actually? Number of threads calculate start. So now I have to find the point where we choose between the timer. Wait. So what line? It was in the function. Do you remember the line? It's here. Plus number of threads. Oh my God! Wait. Okay. Apparently I deleted. Apparently I deleted what I wanted to show you, but I put it into PowerPoint. I put it into PowerPoint so we could just copy it from here. Okay, so now this as you see is the one that goes by the column, because we increment I by the number of threads, right? So actually we can run this. So we go, let me see, CD, where am I? No, I'm actually already in the right position. So we can compile this by, let's go here, by calling make. I'm not sure this was saved. Let's make, do make. So, and then because we are now not in the bin folder, I go to this, which then will be, what was the name of this? This is Laplace, I believe. Okay, I go there, bin ls, so, so it's Laplace 2D and we'll have threads. Okay, now, I started with one thread, which is of course, let's start with 20 threads. Okay, so what we see is we get roughly 300 noops. So if we just run with one, so we get something, something like 100. So this is not really very fast, I guess. Yeah. So let's try out the other one. Let me see whether I've copied this correctly. Yeah. So now this will go over the line. So we'll have the increment. It's a little bit longer, sorry. And we increment I plus 1, so we are in the fast loop, and this here looks a little bit horrible. The condition for breaking the loop is now looking whether okay, so what I did here is we potentially have the problem that if we cut up the system like this and divide the size of the grid by the number of threads, this may not fit actually, right? So if there's a remainder, yeah, so we'll have to take care of the potential remainder, and for this I check here whether we are already in the last slice. And when we are in the last slice, so this here, thread plus 1 is so, okay, I check whether we are still not in the last slice. So when we are still not in the last slice, we take the thread ID plus 1 plus inner crit size. So this is where the other one the next thread would start, right? Yeah, because we start from thread ID times inner crit divided by num threads. Yeah, so then we are supposed to end by thread ID plus 1, right? Yeah, times inner crit size divided by num threads. So, and if we are the last one, we just go to the end of the domain. Yeah, so this is why I use here this this question mark operator. Yeah, so this is what happens if the condition. The first is what is happening when the condition is true, and the second is what happens if the condition is false. So now I turned the other one here off, and now we can go again to CD and call make again. We have to save it, yeah. So then call make again. Then we can go to this folder bin again and run, yeah, just run it with 20 threads, and you see, this is what by intuition we would have expected. So the other one was in the range of 300, yeah, when we are misaligned, and this is now more than twice as fast. Okay, so I have to apologize for getting this completely wrong last time. You see, yeah, it is, you can easily fool yourself, yeah, with some explanation. Oh, this has to be something with the, you know, you will always find an excuse why something doesn't work, right? Okay, so now this has been the correction to this, and now we come to the actual topic of today's lecture. We're still here. So now we come to the topic of the lecture, which is the AVX, Advanced Vector Extensions. So anybody familiar with this already, or is this completely new? So AVX, yeah, is something that exists for some quite time, and it's part of the x86 architecture. Yeah, so it's not the very first. So with the computers with which I grew up, they didn't have these things. But the funny thing is that for quite some time, actually, so that there were predecessors of this, which I left out, but already from the 90s onward. So I guess before many of you were born, the usual Intel CPU already had SIMD instructions. Yeah, so you could use your ordinary CPU in your ordinary PC to do SIMD parallelization, and whether this has been done a lot or not could be up to debate. So the early versions of this was called MMX, and then the ones that we are now more interested in, because we are going to use them today, is the AVX extensions that were introduced first in 2008 for floating point operations. So they use 256 bits registers with which you can do vector operations on 8 floats at a time. So this was then extended, in particular, to integer operations and also to double operations, 2013, and then 2016. There's from 2016 onwards, there are broader registers with 512 bits, float and integer. So 2016 is something that sounds like it's 8 years ago, but it is still in the recent history, right? So not all your computers will support this extension necessarily. In particular, Phoenix is 10 years old. So Phoenix does not support AVX 512. This is why in this lecture we'll not use this. Yeah, this AVX 512 has, of course, a lot of advantages. Biggest advantage, of course, it's broader. Yeah, so you can use bigger vectors, which you, of course, want to do. But it also has additional operations that make sense, and which were kind of missing in the previous incarnations of this. So you can look up by various means what extensions are available on your system. For example, you can use this grep operation here to look in CPU info and get information on what is available. I've already done this, so let me just. I have to look these things up. I'm not a bash scripter. Good, yeah. So this is something that looks into the CPU info whether there is AVX, and now it takes out these AVX extensions and eliminates double occurrences. Yeah, and what you see is we have extensions with AVX and AVX2, and we have no AVX 512 on this machine, yeah, because this machine is too old. Okay, but we'll still be able to use AVX2. Yeah, so probably a little bit out of date, but anyway, let's try to get the hang of it. Okay, so how does it in principle work? So there are specific data types, yeah, which are these vectors, and they're indicated by _ m 256. This is the size of the number of bits, yeah, and if there is nothing else here, it will assume that this is a float, yeah, because this is what these operations were originally meant for, yeah, that you do a 32-bit single precision float operations. So then, if you put an I here, then you have integer, 32-bit integer, and you can put a D for double. Then you have, of course, only 4 float 64, and then there may be other data type, for example, integer data type, a shorter integer data type, yeah, what is short and char, yeah. So which again would have the same number of bytes, yeah, but have a larger vector in principle. So as it is usual with most vector processing units, they cannot address these memory at an arbitrary location. Yeah, they must always be aligned. So these vectors must always be aligned. So what does it mean? Vectors need to be aligned. So your memory somehow starts with an address 0, yeah, and then then each byte has its own address. Yeah, so the bit doesn't have an address, only bytes have address, and and then you have the address number, which back in my time, no, okay, how old am I? So we had I actually had 8-bit computer, yeah, survived 16-bit and 32, but your smartphone may have 32, now we have 64, yeah, so we have addresses with 64 bits, yeah, and when we count up the bits, we go 1 byte further, yeah. These vectors, in order to be worked on, they cannot be any of these bytes, yeah, but they have to be aligned with the beginning of the memory by a factor of 32, yeah, because they are because 256 bits are 32 bytes. Yeah? I hope this is correct. Yeah? Right. Yeah, that's correct. So, which means that your memory did I wait? So by 32 bytes, this means that the 5 least significant bit must be 0 in your address space. Okay, did I misdraw this picture, by the way? Because I was kind of 32. What is 32 bytes in bits? So it's times 8. 265. 56. Okay, I was kind of in the impression that they can be overlapping by, that they can overlap, these things can overlap by half the address space. 200. Okay, you see, I'm making a mistake again. Yeah, maybe I have to revise this picture. I have to think about this picture again. Yeah? But anyway, the message is that the vectors that the vectors need to be aligned in the memory in order for this to work. Okay, so this is also in other vector machines. This is usually the case. So how does it look like? And now you'll, oops. How does an AVX look like? So in order to use AVX, we have several, there are several possibilities. One possibility is you trust your compiler, that it optimizes it to do, that it automatically optimizes it for using vector operations. This usually doesn't work. So what you usually have to do is to tell the compiler exactly what operations it is supposed to use. So what machine operations it is supposed to use. This is the assembler instructions. Yeah, and this we can tell them by including, in order to use them, we have to include the header for the intrinsic AVX instructions. So in the intrinsic, they are here highlighted in red. So suppose what we want to do is we want to add two vectors, A and B, and store it in the vector C. What we would do in this function here is we declare these vectors M, so underscore underscore M 256. So there's no I and no D, so this means it will be interpreted as floating point vectors, vec A, vec B, and vec C. So here we are defining the vectors. And then we can, so the important thing is when you look at the loop, so we'll do this n times. Yeah? If you look at the loop, we increment by 8. Yeah? So because if you increment, if you want to read, so first you have to load the arrays. If you want to load the array, and so each array is loaded with 8 floats, right? So we'll increment this by 8. And in this case, so we take this load function, which looks a bit strange, underscore mm256 underscore load do. Yeah, so this is load u underscore ps. What the fuck? So what this means? So okay, we are loading 256 bits. Yeah, and this u means we are loading from unaligned memory. So the vector itself always has to be aligned. So the question is whether the memory we are reading from also has to be aligned, right? So and in the old days, this made a big difference when they introduced this. This made a big difference whether you load from an already aligned memory or from an unaligned memory. Therefore, there are different instructions reading from aligned and from non-aligned memory. And this U is now helping you to ignore this more or less. So the U is from unaligned memory. There's the same instructions without the U. Then you have to take care yourself that the memory is aligned. Yeah? So here we don't care about whether the memory is aligned. And what we are loading is packed singles. PS means packed singles, and single means single precision floating point number. Yeah. So and now we get here the address operator of the address. So we generate a vector. We'll take the. Yeah, we take the first element of AI and generate a vector from this. Yeah, so pointer to this particular element. So we do the same thing for B, and then we add the vectors. And here's what the fuck again. Sorry, should I cut this out? But really, so if you want to add vector A and vector B, is what you have to do is you have to call this function MM256 adds packed singles, yeah, zack. Then they will be they go to vector C, and now since you have done it, you will write all of this back into the vector C by store unaligned packed single in this address. So and then the last thing you have to make sure is that that you call the compiler that you would actually like it to compile it for AVX2. Yeah? So otherwise, of course, it will assume you want to run it on any machine. Yeah? So AVX2 may not be available in any machine. So if you compile it and try to with AVX2 and you run it on a machine that does not have this, then it will not run. So this is why you need this flag here, MAVX2. Okay. this, unfortunately, this is as strange as it looks. Okay, so we have this load and store instructions. Yeah? As I just said, there is this U here. And so these are not all of them, but I'm varying a little bit here. So there's 200 instructions. Yeah, and so just to try to get the meaning out of this. I guess I believe there must be an I. Okay, I hope so. So this here will load packed singles in an unaligned fashion. So the vector is of course aligned, but the vector we are reading from, yeah, this float const memory address, this may be unaligned. So the last 5 digits, the last 5 digits of the address don't need to be 0. You can have this with signed load signed integers. Yeah, this is SI 256. So actually, because you're just loading memory, this doesn't really matter that much. This is just for your compiler to keep track, or for you to keep track of what data type you're using, because loading data just means that you get this chunk of memory, moving it around. So it doesn't really mean, it's not really important whether here's an I or not, but technically there should be an I here. So load integers from a const memory address. So this loads 8 32-bit floats from aligned, not floats, oh god. Sorry for my... So here, when we write this without U, yeah, so then we have to have aligned. We have to have the memory already aligned. Then we can also store things, so they look the same thing, store with a U, and for example, if we want to store doubles, then we want to have packed doubles. Yeah, so this is a void function, because this gives, so there's the double goes in here and the address goes in here. Yeah, so this is like we are usually doing it in MPI. Yeah, so there's no outcome. No outcome here. This function puts the memory in its particular place, and this will store, of course, only 4 double precision numbers. Okay, so before you do anything with the vectors, you first have to generate the vector, you have to read it from memory, do something with it, and then you can write it back to the memory. So these steps you have to do by hand, and then there are a lot of arithmetic operations, roughly 200, including also the reading and the writing. So once that may be used, a few that may be useful is adding numbers, multiplying numbers, subtracting numbers, and now you have this in the different formats. For example, with packed single is floating point numbers, 32-bit floating point numbers. So add packed singles, multiply packed singles, subtract packed singles. You can add and multiply and divide packed doubles. And the integer operations, they look a little bit funny. They are called extended packed integer 32 bits. So with integer, there are several precisions of integer too. Yeah, you have char, yeah, 8 bits, 16 bit, and 32 bit, and also 64 bits. Yeah, so here you can indicate which one you mean. So this is an intrinsic multiplication, and then there are other types of multiplication. So these are now really machine operations. So for example, there is multiply lower extended packed integer 32, which means we are multiplying two integers into two 32-bit integers into a 64-bit integer, because when you multiply numbers, yeah, the result is larger, and then but you'll want to return a 32-bit number, so you just return the lower 32-bit. Yeah? So you can be as specific as this, or you actually have to be as specific as this. So you want to multiply, so how do you want to multiply? Yeah? So what do you want to do with when you run out of bound, for example? Yeah? So they have to indicate this. Okay. It is really surprising to me why nobody thought about a more convenient and natural way of writing down these operations. Like, vector 1 plus vector 2. Yeah, so this is not the case. So you always have if you want to write an equation, you have to write it in this way, which is probably one of the reasons why this is not so common. Okay. This brings us to our example, I guess, which is matrix multiplication, which we'll use for both the rest of this lecture and later for the example. And I believe I don't have this here. Okay, yeah. So, okay. Now probably you want to start your computer and take this file here. So we are usually we are coming into this folder, into the home folder. I have so in this PVR 2024 there's Gaia, and then there's lecture 9, and then there's matrix multiply.cpp. And please take this, don't modify this file, because this is my file. Take this and copy this into your folder. Okay, we are in lecture 9, I guess. So, let me go to Laplace. No, this is CD lecture 9. And I probably have a bit of nonsense here already. Yeah. So, matrix multiply. Now what I'm going to do is I will save this file as matrix what am I doing? Matrix multiply AVX.cpp. Okay, so now I made the copy myself in order for this to that I can modify and keep the other one where it was. So let me see. We'll have to get C++. So let me just see whether this works. AVX2, and we'll have the file matrix multiply AVX, which does not yet include any AVX, and I call this mat AVX. So let's just see whether this here works, and let me run it, mat AVX. So that's okay. So does some funny output, and we see it takes 1 second. Okay, let's briefly go. Let's briefly go through this code here. So what I just recognized, even though it was not supposed to be here, it is here. The header for the intrinsic function is already here. Yeah. So this is something that we always need when we do AVX. So then there is a print function which we are not taking a lot of care of today. There's a main function that generates these matrices A, B, and C. And here we are coming to the allocation of memory. So, and I think this is new to most of you. Who knows what this malloc means? Let's briefly go back to, Yeah, so let's briefly go back to where we have been. So what does malloc mean? Memory allocation. Yes, so we are allocating continuous blocks of memory. So to understand how this is working, or how your computer is managing its memory, there are in the wrong position. Right, so this is where we wanted to go. So there are two, maybe a little bit simplistic, but in principle there are two places in memory that are managed by your program. One is called the stack and the other one is called the heap. So the stack is something rather intuitive. The stack is the stack is a position in memory where you have enough space on top. If you run out of space, you have this stack overflow thing. Yeah. So what you do is whenever you generate a new variable, this variable will be put on this stack. Yeah. So because the compiler knows what size your variable is, because it knows the type, it will put it. It knows what the last, so it has the last address from the last variable, then it increases the stack count by the size of this one variable, and then it puts the next variable, and so on and so on. So whenever a new variable is introduced, it is put on the stack. And now this is also related to the scoping. Yeah, you know there is this, there are these scopes that are indicated by these brackets. Yeah, and the new variables that are inside this scope, yeah, they become invalid once you run out of the scope. So, for example, in this here, so you have, so in main, Yeah, so you have first, you have this int a, which is this is int star. This is a pointer, so it's not. It is the address. It's not the information on the matrix here. It's only the pointer, so it has on a modern computer. It has 64 bits size, yeah, and then there is a matrix. Do we have print matrix? Print matrix? Int matrix? Okay, I don't see where I have this int matrix. Print matrix. Okay, I don't int row. Okay, maybe there's not completely this example, unfortunately. Sorry. Yeah, but anyway, whenever you put a new variable, it will put on the stack, and when these variables go out of scope, yeah, your compiler knows where the scope started, and it will discard everything that is related to that particular scope. Yeah, and so the stack will be cleared again. Now the stack is this dynamic thing. So when you call a function, for example, the arguments to the function are also put on the stack. When you go out of the function, these arguments are discarded from the stack. Now, if you want to have some continuous memory or memory that an amount of memory that you do not know its size of at compile time, then this doesn't work. Yeah, because the compiler doesn't know the size of this stack. So you have to find a place in memory somewhere else, and this is called the heap. So you ask your operating system, can I have memory somewhere else? And this is of a certain size. Yeah? And this is done by this malloc function. So yeah, so we'll the malloc function allocates a chunk of memory somewhere in the heap. There are also a little bit different malloc functions, aligned malloc, that can, for example, take care of aligning the memory with these vector constraints. So, for example, that the 5 least significant bits are 0 of the starting address, yeah, which is in general not possible to have it on the stack, because where you are in memory on the stack always depends on what has come before you on the stack. Yeah? Okay, so this is something that we need, and this I probably jumped over this. So this is what we want to implement. You, please.
What's the difference between malloc and new?
What is difference between malloc and new? So new is a new way of mallocing, of allocating. So malloc is, so from a historical point of view, malloc is a function coming from C. Yeah? And new is from C++. Yeah? It is, so new takes care of the allocation of your object, and from which the compiler somehow determines its size by the constructor. So the constructor of your new object has to tell the compiler somehow what is the size that has to be allocated, yeah, for this object. And then there is, of course, the inverse too. Yeah? So you have the destructor, delete, yeah? And here, so this is the newer version from C++, which is already 30 years old, yeah? But anyway, so C is 50 years old. So the old version of the destructor is this free command. Yeah? So you have allocated memory and then you have to free the memory again. And it's the same thing as in C++. If you don't free your memory, you have a memory leak and your application will kill your computer after some time. Okay, thank you for this question. So now what we are supposed to do is to calculate the multiplication of the matrices A and B, and this gives us, so they are both size nn, and this gives us a new matrix Cij. So in mathematics, we always count from 1, and in C or in C++, we always count from 0. Yeah, so we'll have to take this into consideration. So what we like to do is, because we want to unroll this matrix, because in memory is always one-dimensional. Yeah, so have the row with C I times n. This is our row. I is the row, and plus j is the column. Yeah, so we'll count over the column, and now we'll have to implement this multiplication like this. So this is our what we want to do. Okay. And now let's go there. So you see this is an integer matrix. It could be a floating point matrix, yeah, but we're using now an integer matrix. Integer, we'll have an n times n, yeah, so n times n size of int. So the important thing is we have to tell malloc what amount of memory we want. Okay, they are square matrices multiplied, they're all the same size. We initialize them by random numbers with a random seed 0. Okay, yeah, we have a random seed, yeah, and then we take a random number modulo 10. So we get some numbers in here, A and B. So now I printed the matrix. This is here, up here I have a print function for the matrix. It's not very important. I print the matrix. And then in order to see how well we perform, I start a clock here. Then I do the operations, which is a nested loop, 3 times loop, calculating the new C matrix. Then I'll call finish, give out the time, and I print the matrix C. And then at the end, I have to free the memory A, B, and C. And then I write out the runtime and return 0. Okay? So nothing completely fancy. So now what we are going to do in the last half hour or so, I don't know, is we try to implement this using AVX. So we see without using AVX, it takes, we have a matrix size of 512. Yeah, so I've taken care of that we can divide this by 8, right? Otherwise, we would be a little bit in trouble. So, and multiplying these matrices takes 1 second. This was the runtime. So let's see whether we can accelerate this. So first of all, we have the intrinsic functions implemented. And now we want to vectorize this thing here. So now again we have 3 loops. My typical question, what would we vectorize or what would we parallelize, the outer or the inner loop? The inner loop. Okay, let's try to vectorize the inner loop. Yeah, this is also the only thing that looks reasonably simple, right? So let's take this thing out and say we want to vectorize this inner loop. Now here we have again for int k is equal to 0, k is smaller than n. And now there is of course a difference. Now previously we counted up k always by 1. So what do we have to do now with k? We have to increment this by 8. So k equals to k plus 8. Yeah? So then we get to
k also goes to n divided by 8, right?
no.
Okay.
No, I mean you could do it like this, but then you would have to increment by 1. Yeah, so of course there are different possibilities. Why is this here underlined? I don't know. Okay, now we want to implement our loop in here. However, before we can do this, we need our vectors. We first need our vectors, and the way we indicate these vectors is by underscore M256, and we want to have this an integer. Yeah, because we are now doing operations on integer. And we call this vec A, vec B, and vec C. Okay, so this is our data type here that we are going to use. And then we need to do the loading first. So we need to load vector A. We need to load vector A, and vector A is, well, okay, we have to look at what we have here, right? So A is A of I times n plus k. Yeah, this is what we want to load. Now we need to have one of these fancy load operations that go in MM2. Here actually you see all these functions that are available. Okay, you see it starts with apps. Yeah, right. So by the way, here you see we have integer, 8-bit integers, 16-bit integers, 32-bit integers, and 64-bit integers. There's all available. Yeah, we want to load. You see, we have load functions without u and load functions with u. Yeah. Now, in this case, because we did not take care that the data is aligned, that we put into it, we have to use the unaligned version. And we continue with signed integer 256. Okay, and now what we have to do in reading, now we have to read actually an M256 integer, which the data A, so our matrix A is not, but it's already in format of an integer. So what we need to do here is an explicit cast. Let me see now. An explicit cast. Or is it called a static cast? Constantine, how is this called? This is, we have to cast this to M256I pointer. Is static cast. Or, yeah. C cast. So, anybody completely unfamiliar with what cast means? No? All clear what casting is? Okay, good. Then I'm not going to explain it any further. And now we get to the address operator of A, and now we have to do what we had here in this non-parallel version. Yeah, this is I times n plus k. Okay. So, and don't forget the semicolon. So now we loaded A. We had to cast it into this vector format. Yeah, because otherwise it wouldn't accept it. Because C++ is, of course, a typed language. I mean, in principle, from a physical point of view, it doesn't really matter because you're just moving memory, right? Yeah, but here it's it is necessary for the compiler to accept it. Okay, now we do the same thing for B, but B is not exactly the same. It is k times n. We read it from k times n plus j. Okay, and okay. You know what, guys? This is wrong. Why is this wrong? Because it will read yeah, okay, so this is what will this read? Yeah, so it will, it will then read the next 8. Yeah? So it will increment j and not k. Right? So then, which means my thing here is wrong. So what do we need to do to make this correctly? Okay, what we can do is we can now be stupid and say we get int log b, int log b of the size what does it do? So, no, not that one. How am I doing this correctly? I'm not the everyday programmer apparently. Is it log b and then 8? Right? Yeah. Okay. So in this, now what we need to do is to, I mean, either we write a loop or we'll be very stupid and just write 0. Should we write a loop? It's maybe better to write a loop for int. So we are running out of indices. I is equal to 0. Actually, it's not efficient to write short loops, but anyway, yeah. I smaller than 8. I plus plus. So we say that log b I is equal to this here, and this is k plus I. Okay. Do you agree? That we now put this into this local II? So this means we can have this here as b 0. So now I'll take wrong away. So our problem is that the b vector here, yeah. So the data that we want to process sequentially is not in sequence. Yeah. Okay. So you see, it's already getting a little bit complicated. Yes. Thank you. So log b. So now we put this into the right memory, hopefully, and now we want to do our operation. So we'll have multiplying elements. Multiplying. We do vec c. Now we do the operation. No, it's only one underscore for this. It's only one underscore MM256. And we do a multiplication. So there's several multiplication. You see there's high, HRS. I actually don't know what this is. Now we are using the lower. So this does the multiplication of two 32-bit integers, and we're keeping only the lower 32 bits. So if we don't run out of bound, which we will not because our numbers are in between 0 and 10, yeah, so we'll not run out of bound. Then we take, then this will be correct because we take the lower part of it. And we do this extended, let's see, I have to look these things up. Extended packed integer 32 bits size, and we do this on VEC A and on VEC B. Don't forget the semicolon. So, then we'll have, so now what do we have now? The C that we want to calculate in this loop here is one number, right? Now we have 8 at the same time. We've done 8 at the same time. However, we have not, so they are supposed to be summed up, but they are now not summed up so far. So what we have to do is again to sum over this vector. And unfortunately, this is a function that does not exist in the AVX2 version. So there is a function for this in AVX 512, but not in our version here. And this is very inconvenient because this is something that you need a lot of time. So what you have to do is you have to unpack the thing and sum over it again. Which, yeah, you are smiling because maybe this all makes the entire thing a little bit, ridiculous at the end. We'll see whether this actually helps us. So we need a result, yeah? So let's say we have an int result. So I've just learned that I don't know how to write this. So now I try to write it correctly. Yeah, so an integer again of the result. And then we store our result sorry, it's only one underscore, so writing it back, 256, store, with you or without you, who is in favor for you? Who is in favor for not you? So why do we need the you? I mean, first of all, it makes life simple, right? Second thing is we have put this here on the stack, and we have no way to know whether the stack is aligned or not. So it could work. So we have a way to do it because we could. Okay, we don't know where the stack started, but when we know where the stack started and we count our variables, we could potentially know where we are, yeah. But we don't know, so we take a u here. Now we write signed integers 256. So and then we'll do this casting again. So for the casting, we need 2 underscores, M256, integer, vector to it, into result. And here we store vec c. Now we stored vec c, and what we now want to do is we'll take c, let me see, so cin plus c, so what is written here in line 48, I n plus j plus equal, so we're incrementing this, and now we have to go over all of them. Okay, so we could do this by a loop. Actually, some of you should do it by a loop, and some of you should do it by not loop, yeah, because this may be doing short loops is very inefficient usually. So this is why I'm now going to write this out by hand. So this is, of course, there may be mistakes. 4, 5, 6, 7. So now we summed all of this. And then we are done. Oh my God, is this complicated? So who of you took a loop? No loop.
But it shouldn't make a difference. The compilers are quite good at loop anyway.
Yeah, so maybe, for example, the question is whether it does the, so because we already have these other loops. So for example, this here, the compiler should unroll this, right? Yeah. So now we have done it once this way and once that way, yeah? Okay, let's, so we are inconsistent, yeah? So do we want to try what happens? So of course we have to compile with AVX2. It compiled. Okay. It compiled. By the way, we don't know what is the right result, so we will not see whether we made it correct or not. Now you can, for example, you can remember that the last number here was 9,619. Let's see whether we get this again. So time was 1 second. Oh. Yeah, so the result looks the same. The runtime also looks the same. Okay, we can try increasing the number of elements somewhat. Say we need to 1024. It needs to be. Yeah, but then we have to. So then we have to wait longer. Now it's doing the calculation. Now it takes 7 seconds. So now what do you want to compare? When you want to compare this, then what we need to do is to, see, this is surprising. So there's this, actually it's only one line, right? And this is what we are doing instead. And save. So what was it? 7 seconds. Okay, so this took 8 seconds. So apparently we got it a little bit faster. So the reason, you see, the reason why this doesn't work so well is because the important stuff is this misalignment of this second matrix. Yeah, so when we go back and take this in here, so because the operations are usually not so expensive. So this would be the AVX. So because unfortunately we have to do this stuff here. Yeah. By the way, we did not use any optimization. I don't know whether we use U02. So this will tell it to optimize it. Maybe, loop unrolling. If you don't tell it to optimize, then it will not unroll the loop. Yeah. So let's try it with this configuration. Whether this makes any difference. We get another 7 seconds. Oh. 3 seconds. Wow. Yeah. Okay. Now we can. Okay. So this is now with optimization on, but we hadn't. The optimization was off in the other case too. So what we wait. I'm not in the right place. Oh yeah. So what we can do again. Turning this here off. And turning this here on. Save. So now it was 3 seconds. 3 seconds. See, AVX is astonishing annoying. Okay, now, by the way, now we have only few minutes left. Yeah. So, but I think I have a few things that I wanted to say before we go to the break. Shortcomings. I mean, you could say, you see, so much work for nothing, right?
Professor.
Yeah.
Try not to print the matrix.
Yeah, but the printing the matrix was not included in the timing.
Oh. Okay. No.
Yeah. So, yeah. So in principle, anyway, your compiler should do this, should use vector operations intrinsically, automatically, I mean. But this rarely happens, really. The instructions are really, really cryptic. I think this is the most annoying thing, because in CUDA, which we'll see next week, this is much more easy and it actually works and it's actually faster. Yeah, and it's the same idea. Yeah, so here we do not have any possibility for branching. We can simulate branching. I will show a very brief example in a minute. Then there are other things that may be a little bit strange. So your computer uses a lot of power when it does this, and many processors have dynamic clock rates. So when they consume more power, they downregulate the clock rate, which means they become then slower when you do vector operations, potentially. Yeah, you don't know, maybe depending on the weather. Yeah, and of course it's not everywhere available. And yeah, the lack of a Scala product, I think, is also a big problem. So when, yeah, not everywhere available. The thing with these vector things is, well, yeah, some people think that the numbers, that the days of x86 is kind of numbered and will disappear anyway. I don't know. The thing that I know is when I started to be a PhD student 20 years ago, there was a machine that was called AVX. Does anybody on Earth remember AVX? I mean, you're much too young for this. But this was the Apple processors, PowerPC processors. There was a thing that was called G5 back then. So and then this had vector unit that was called the AVX. Could only do floating point 32-bit operations, and people said, so the ones who were believing in Apple back then, they said this is the future. Yeah, and there was exactly one processor that supported this. So there was a G4 that did not support it. The G4, there were two processors. G4 was PowerPC, G4 was supporting this. Then G5 very briefly supported this and disappeared, and then they went to Intel, and then everything disappeared around this. Now, I started being a PhD student at the G4 time, and my doctoral advisor was completely on this track and wanted me to implement my code on AVX. Yeah, so you have to go through all of this by hand so that it is supposedly fast. And good for me is that the AVX disappeared quicker than I could actually start programming. So, and this was a message for me, but I had a similar opinion about CUDA 15 years ago, and I have to agree that CUDA is very much alive. Okay, last thing for the lecture today is this SIMD on principle does not allow to have branching, but you can simulate branching, and this is also what happens in CUDA. So in CUDA, for example, there's no problem writing branching, writing if statements also. Yeah, this will take care of it below, but you have to know it's simulating an if. It's not actually doing the if. So here this example is you're looking at vectors element by element. Yeah, if an element is larger, if A element is larger than the B element, so the result should be plus, otherwise it should be minus. Okay, so synthetic example. Yeah. So the way you can simulate this is by using masks. So say you start with vector A and vector B, and then you can generate with one of these 200 functions that are implemented here on the processor, you can make a comparison, and with this comparison you can build a mask. And so you need you need a vector, again, that is this mask. And this mask is generated by this function working on integers. So there is a compare, so this CMP, my interpretation, I believe this means compare. And GT means greater than. Yeah, so, and then there are others, yeah, equal to, yeah, and so on. So this will compare greater to, and then will generate a mask. So when this condition is true, it will fill these vectors with these slots with ones, and if it's wrong, it will fill it with 0, right? Then what you do is you do the then branch and you do the else branch. You have to do both. Always have to do both. Yeah? And then you merge these two results by another function that is called blend. So the blend function takes the first result and the second result and the mask where it decides when the mask is here 1, yeah, so I take so it takes the else branch first, apparently. So if it is 0, it takes its first argument. If it's 1, it takes the second argument. Yeah? And then it merges this together, and then you have simulated an if then else. Okay. So that's about this lecture. I'll stop the recording, and or do you have a question that, yeah?
Yes. Somehow it seems to me that AVX works as non-P arrays, meaning that there is a function that can take read a for, or the idea is to not use fors. For example, if we wanted to do, I don't know, just the comparison of both, we would need a for loop, and then we would need to iterate for each of them. And here we have just a function that allows us to get rid of the for. And in the example of
free of the okay, so you of the loop, yes, yeah.
Yeah. And in the example of the matrix multiplication, we have still 3 for loops, but right, we had one for that went over I.
Yeah, so we reduce the loop. So if you go back to so why we still have the loop, yeah?
Mm-hmm.
So we still have the loop. The thing is instead so the loop is still here, right? So but we are taking steps of 8 each, right? Yeah, because our vector is of finite size. Yeah. Okay. So then with this, I'll end the recording. If my computer lets me to end the recording.